Today we will discuss about a basic operational amplifier topology in the negative feedback sense, which is that of the inverting amplifier. And this is one of the simplest operational amplifier topologies other than the voltage follower. So herein the input signal is symbolized by V sub I, the output is symbolized by V sub 0, and there is a feedback resistance between the output and the negative input terminal. And because this feedback element is connected back into the negative input terminal, hence the name negative feedback. So in this case, we are using a resistance of value R2, and there is an input resistance R1 which connects the input signal Vi to the inverting input terminal of the op-amp. Also note that the positive input terminal is connected to ground. So the idea behind solving these sort of circuits is to be familiar with two basic concepts. The first one is that of virtual short, and the second one is related to the infinite input resistance of the operational amplifier. So if we restrict our understanding only to the ideal case, of course it's an abstraction, but with an ideal case, virtual short simply implies that the voltage at the plus input terminal is equal to the voltage at the minus input terminal. And so what it implies is that the voltage at this input terminal, that is the non-inverting input terminal, is the same as the voltage at the inverting input terminal. Now, this arises due to the infinite voltage gain or open loop voltage gain of the operational amplifier. And in the present case, we can see that because the non-inverting input terminal is connected to ground, therefore this is at 0 volts, and therefore at V minus we should also obtain 0 volt. So this is the first concept. The second idea is that of the fact that if the op-amp presents infinite input resistance, then no current can enter the input terminal of the op-amp. So again, this is an ideal case, and herein we find that I is equal to 0 for both the inverting and the non-inverting amplifiers. However, note that one of the major mistakes that students make is when they consider the fact that the output terminal also doesn't draw any current. But this is not correct. The operational amplifier has the ability to sink, or it has the ability to source. So sinking means it can draw current into the input terminal of the op-amp, and sourcing means it can source current into whatever the load is present at the output terminal of the op-amp. So note that I out is not necessarily equal to 0. Now, if we use these two concepts, so right at the beginning, we found out that if the voltage at the plus terminal is equal to 0 volt, and the voltage at this node should also be equal to 0 volts, and therefore if we consider that some current I1 flows due to this voltage source Vi, so this I1 should only be able to flow through R2, because the op-amp is preventing any current flow into its input terminals. Therefore, if we write this outgoing current as I2, then simply I1 should be equal to I2, and then we can apply Ohm's law. So just briefly recall that if this is a resistance given whose value is R, and the voltage drop across its two ends is V sub R, and the current that flows through this resistance is I sub R, and then notationally if we can write V sub R as V sub P minus of V sub Q, so this is the voltage difference between its two nodes. Therefore, from Ohm's law we can state that V sub R is equal to I sub R multiplied by R, and therefore the current through the resistance is equal to Vp minus Vq divided by R. So this is simply equal to the voltage from the node from where the current is flowing to the node to which the current is flowing divided by the value of resistance. And therefore, for I1, we can formulate the current as V sub I minus of 0 divided by R1, and this must be equal to 0 minus of V sub 0 divided by R2. So if I1 is equal to R2, if I1 is equal to I2, then from this formulation, we can go one step forward and find out the expression for the output voltage V0 as negative of R2 by R1 multiplied by Vi. So note that the gain of the circuit is given by R2 by R1, and this is a ratio of two resistors. And the implication of this negative sign is that it will lead to something called as polarity flipping. So for instance, if you consider that R2 is equal to 10 kilo ohms, and then let's say R1 is equal to 1 kilo ohm, then V0 is equal to minus of 10 kilo ohm divided by 1 kilo ohm multiplied by the input voltage Vi. And so this becomes equal to negative of 10 times Vi. And of course, if these are time dependent functions, if Vi is a time dependent function, then V0 should also be a time dependent function. And we can write this as V0t is equal to negative of 10 times VIT. Now consider two cases. Let's say we consider a DC case first, and let's assume that the input voltage applied is equal to 1 volt. So the voltage applied to this node is fixed 1 volt, and therefore the output voltage will be equal to negative of 10 multiplied by 1 volt. So V0 will be equal to negative of 10 volts. So if this is your V0 axis with respect to time, we obtain the output voltage as negative 10 volts. And if we consider another example, say this time we consider an AC signal of, let's say, 1 sine omega t, so the amplitude is equal to 1 volt, then the output should be equal to minus of 10 sine of omega t. So note that when the input is going positive, the output will go negative. So there is amplification because 1 volt is getting amplified to 10 volt, and of course on a point-to-point basis that happens. And then if we look at the extrema points, so let's say we are looking at 1 volt, we obtain the output as negative 10 volt. So this idea of flipping of polarity of the input signal to the output is also called as 180-degree phase shift. So here if we look at the phase of this signal, then it is simply shifted by 180 degrees. So it's as if our axis is starting from this point onwards. Okay, next. Now what happens if we make both the resistances same? We obtain V0 is equal to negative of Vi. So basically this is an example of an analog inverter. If you can fix both these resistances to be equal, then theoretically this becomes an analog inverter. And then the question arises that we have something called as a voltage follower, which is basically a special case of the non-inverting amplifier. Now if I have V0 is equal to negative of Vi, and if I disregard the sign, this negative sign, then you can also think of this as a voltage follower. And then if we consider this sign, this acts as an opposite polarity type voltage follower. But there is one fundamental difference between the voltage follower and this inverting amplifier with its two resistances taking equal values, and that is the fact that a voltage follower acts as a buffer. But this circuit, although it is following the input voltage in the negative sense, in the opposite sense, but this does not act as a buffer because it is providing an input resistance of R1 ohms. So input resistance means what is the resistance that this source is looking into this circuit. And so we can find that the resistance is equal to R1 ohms. So this is the fundamental difference between that of a buffer and that of a simple voltage divider, even though it is in the opposite sense.